Hello, you should see the desktop and hear me by now. Does that seem right?
Yeah.
Yeah.
Yep.
Oh, I have my speakers turned off. Okay, again, you can hear me now, right?
Yeah.
Yes.
Okay,
Yes.
I had my speakers turned off for. All right. Most people are here. Okay. Okay, so what we're gonna do today is keep talking about homework assignment 2, the programming assignment number 2. So we start off by, oops. Let me download it. And I also want to download the zip file that has an example that's important for homework assignment 2. Okay, and what we're going to work on today, which is more examples that are important to homework assignment 2. So we have to understand some things about C to understand this homework assignment. Okay, so your homework assignment is to write a program that acts like this launcher. Okay, so if I run the launcher demo, it's like a baby version Explorer. It lets you run programs. So if I choose 1, it launches Notepad for me. Okay, so it's a launcher. It launches programs. Okay, and if I choose 5, it launches WordPad for me. Okay, and if I choose 3, it runs the NS lookup program. Notice it runs it in the same window, just like kind of like a shell would. Okay, so I could look up. See, okay, then I can quit NS lookup, and I'm back to my launcher. Okay, if I choose 4, it runs the character map for me, and if I run 2, it prompts a shell. Okay, but one thing that's interesting is the shell is different when this program launches the shell. This program waits for this one to finish. So this program C is waiting. Okay, so I made this is just to get you used to doing a few different tricks with Windows programs. So in all the other programs, this one just launches the program and then it's ready to launch another program. But for number 2, when it runs the command shell, it has to run the command shell so it looks like this. Notice that there's some things you have to set up. What is your command? Speak up. Okay. Then, over here I can run commands. Okay. I exit this thing. Okay, by saying exit. I mean, I could just close the window up here, but the more proper way to end this thing is to say exit, and you can even give it a value. Okay, so exit 33. When I exit, this thing got the exit value. So that was like think of this as a program calling another program, just like a function calls a function. And when the called program returns, it returns a value to the calling program. So the calling program do it again. This program calls CMD. Okay, CMD does something. Then CMD returns a value to the caller. Okay, see, it returned the value 66. Okay, and this program waits for the return value. Okay, so see, it's waiting for the return value. So it shows you that programs can run programs the way functions can call functions. That's a little bit of what this is about. And in many system administrators situations, that's exactly how system administrators and in things like big data and all that, people use this feature that a program can call another program kind of the way the function calls a function. And the calling program waits for the called program to end. Okay. And it gets return value. Okay. Return value is 3. One last thing, if I call this program, and if you just close this thing, what's the return value? The return value is a weird number. Notice that the return value is a weird negative number. Okay, so if you exit a command program without telling it what the exit value is, the exit value is something kind of weird. Okay, so you have to write the code that mimics this. Okay, all right. Now I give you a little bit of a sketch of an outline, not much. Okay, mostly what's in here is you'll see this is for handling errors. When you call a Windows function and it does something wrong, you use this to get a proper error message. Okay, we'll see examples of doing that. Okay, now the key idea to writing that program is in this baby program over here. Here's a baby launcher program. Okay, it launches 3 programs. There's no prompting or anything. When you run this program, it launches Notepad, char map, and then let's look up. Okay, so it's a baby launcher. Okay, there's no prompting, but the key idea is in here. Okay, the launcher. Remember, we talked the other day about processes. Every process is created by another process, by the parent process asking the operating system to create the child process. Okay, so every process, as a matter of fact, if I do Control Shift Escape, I bring up Task Manager. Here in Task Manager, I have a list of all the processes running on my computer. Every one of them was created by another process calling create process. Okay. Now, remember, Task Manager doesn't show you the parent-child relationship. So to see the parent-child relationship, it helps to use this other program that I put in here, Process Explorer. If I start up Process Explorer, a lot of information in Process Explorer. Let's see. Over here is the tree view of all the processes. So you have like this tree structure you can collapse. Let me collapse everything. Okay, this is the top level now. Okay, everything is a child. Every process running on my computer, if I go back to Task Manager, every process, and there's lots of them, is a child of these. Yeah, somehow when Windows started up, these were the processes that ended up being the top level processes. Now, some of them don't have children. Some of them are important processes that don't have any children. And then like this one is part of the operating system. It's only got 3 children. Okay, this system is something to do with the operating system. It's got 3 child processes. Okay, this one, it's got 2 child processes, and it got a child process with a whole bunch of child processes. This is the services. This in here is the services, which in Task Manager is actually this tab over here. These are the processes they're special system processes called services. Okay, so all these service processes, I mean, services, things like a database service, a web service. Okay, you don't have a database running on your computer, but you do have a lot of these weird services running in the background, part of the operating system. All those processes are actually living in a branch of this tree over here. So there's the service processes running in that branch of the tree. Okay. Then here's process, which is 3 child processes. It's got to do with logging into the computer. Explorer is where almost everything else is. Because Explorer is the thing that's my desktop. It lets me launch processes. So if I launch processes by double clicking, so I just launched that guy. I launched him using the Explorer because I double clicked. Let's see, where did he end up? I think oh, there's 2 Explorers. Oh, I don't even know why there's 2 Explorers. Okay, so the one The one we're interested in, the desktop, would be this other Explorer down here. Don't know why Windows has two Explorers running. So I don't know the difference between this Explorer process and this one. Okay, so there's an Explorer process with some stuff running under it. Okay, something to do with the graphics card. There's a CMD running that's running Java. I think that's the Java update. I think that's the Java update process. Oh, okay. Now let's go down here. Here's the Explorer. This is my desktop. Okay. So see, my copy of Chrome is running under here. My copy of Zoom is running under here. My copy of TextPad is running under here. Process Explorer is, because I started all of them from the desktop. So if I go back over here and I start that editor, see, you see that little green? See, when he starts up as green. If you watch over here, it'll turn red when I close it. See, it turns red and then disappears. When it's created, it's momentarily shown in green. See, and then it turns regular blue. Okay. All right. So processes I create over here show up under Explorer. Okay. And if I create a CMD in Explorer, okay, see, I created a CMD under Explorer. Now I can use, if I launch processes from it, now it's CMD that called create process. So CMD is the parent of Notepad. So when I type that command here, CMD turned that command into a function call to the create process function in Windows, and CMD became the parent of the process I just created. Okay, so it became a parent of Notepad. Okay, and if I create a WordPad, well, oh, WordPad's not, okay. Okay, if I create a WordPad process, oh, WordPad's weird. Notice it didn't show up here. WordPad showed up over here. Later on, I can explain to you why. It did not end up as a child process of CMD. Well, I can tell you, the reason is, remember I showed you that WordPad's really set up. There's a program called Write, whose job is to launch WordPad. So what happened was when I typed Write here, that launched the Write process. The Write process launched the WordPad process. So that means that Write was a child of CMD and WordPad was a child of Write. But then Write kills itself because it's done its job of launching WordPad. When Write kills itself, WordPad loses its parent, and WordPad moves to being a child of the root. Okay, so you hit Write. Okay, Write launched, was a child of root. Write created WordPad, so WordPad was a child of Write. But then Write killed itself, it exited, and WordPad moved over here to being a child of the root. So for example, if I go over here and kill this CMD, what will happen to Notepad? So I'm going to exit CMD. Notice how CMD died? Well, where did WordPad go? It went over here with Notepad. Notepad and WordPad both went over here. They're now children of the root. When you lose your parent, you don't go to your grandparent, you go to the root. So that's how these processes ended up over here. These are processes that were created by some other process, then their parent went away, and they end up being children of root. Okay. All right. So this Process Explorer shows you all the parent-child relationships. And what's really important is that every single process is created by some process calling the operating system's create process function, and that makes the calling process the parent. Create process is the equivalent of new. Yeah, it's from the point of view of object-oriented programming, it's what creates new processes out of a program. Remember, our other word that we use is a program. If I look at Notepad, Notepad is an EXE file on the hard drive in the C:/Windows/System32 folder. There's the Notepad program. A program is a binary file that's all the instructions, the machine code for the program in a file. And create process takes that data in that file, copies it into memory, and starts a process out of it. Okay. And here, what I just did there was I told Explorer to make a notepad process for me. So over here, that notepad is a child of Explorer. See, that notepad is a child of Explorer, not a child of a CMD, it's a child of Explorer. If I go over here and I type notepad, again, it's Explorer that's launching or creating the instance of notepad. See, it was actually, I was talking to Explorer. When I go over here, I'm talking to Explorer. When I double click in a window like this, these are called Explorer windows. File folder windows are Explorer windows. So I'm talking to Explorer. But if I launch a CMD in this folder, okay, I just launched that CMD in this folder. And now if I run Notepad, okay, the CMD is a child of the Explorer because I used the Explorer to launch the CMD, but Notepad's a child of the CMD. Explorer called create process to launch CMD. CMD called create process to launch Notepad. And one thing, we won't talk about it, but see how every CMD comes with something, this guy here? Con host stands for console host. CMD actually does the talking to the operating system. Console host is the GUI for the CMD. Okay, the Microsoft set this up in Windows Vista, I think it was. It used to be that CMD was its own GUI program, but it isn't anymore. CMD is purely just a program that reads in strings and writes and calls create process. The actual GUI-ness of a CMD is this program called conhost, console host. And it's kind of it's actually closer to the way Linux does things. So CMD really is just a program that reads command lines and does whatever you tell it to. It doesn't even have its own GUI. It needs this guy as a child to run the GUI for itself. And you can actually run CMD in other GUIs. Microsoft now has other GUIs that you can use to run CMD in, and that's where Microsoft Terminal comes in. That's another GUI for running CMDs. Okay, so every time you launch a CMD, you'll usually, well, not every time, but you'll usually see a con host under the CMD. If you look at it in Task Manager, it's confusing because the CMDs are in one place. There's the CMD. See, there's two con hosts. There's three con hosts. One of them belongs to that CMD, but who knows which one? Yeah, over here you can tell because you have the parent-child relationship. Here, you just see there's a CMD and there's actually three different con hosts, and who knows which one is for which. There's some other CMDs floating around. I saw one somewhere. I remember seeing another CMD somewhere. Oh, here's one. See, here's a CMD, and there's its con host. Okay. All right. All right. So now what we want to talk about is that create process function. The create process function that every process uses to create another process. Okay. So we've got, oh, let me close a bunch of windows. I'm just trying to close these windows so they don't get in the way of doing things. Okay. All right. So here is a sample of using create process. Now, create process is a mess. Okay. It's a function that takes 10 parameters. The parameters are all kinds of complicated things. Some of them are not even needed, so you can just null them. Okay. Some of them, this thing's called a bit field. See, there's the bitwise OR. This parameter is something we call the bit field. This parameter is a data structure and it's an in parameter. This parameter is a data structure and it's an out parameter. This parameter is a string and it's an in parameter. So string, bit field, data structure as an in parameter, data structure as an out parameter. Okay. And up here is there's the code that created that data structure. And here's the code that created that data structure. Okay. Now, to really understand, and then down here is some code that uses those data structures. Instead of looking at the details of this process right now, I want to switch to talking about how functions make use of data structures, because this is nowhere near as simple as Java. This is where C becomes tricky. Functions using data structures make C difficult. And one of the design goals of the Java language was to make what is difficult in C much easier to deal with. So we're going to look at some examples that try to show us how functions use data structures. Okay. And we have to, by data structures, I mean arrays and structs. These things called structs. Like, when I say this is a data structure or this is a data structure, technically in C, they're what are called structs. They're data struct, C is from a day when everything was abbreviated. So they're data structures. Okay. But who wants to say data structure when you can just say struct? Okay. So C took the word data structure and shortened it down to struct. Okay. So C has structs, and structs are what in Java became classes and objects. Okay. So structs in C are the equivalent of classes and objects in Java. Okay. So let's go look at some examples. What I mean by we're going to leave this function behind for a minute and switch to another folder. This folder that's from the website, this one, working with composite data. Okay. Okay. So, oh, and I've been giving you a bunch of readings, and we're kind of talking about those readings. Chapter 7 on arrays, and this chapter 5 in the other book, arrays and pointers. Arrays are one kind of composite data because array is made up of lots of array entries. And now we're going to talk about structures, which are another kind of composite data. So structures are made up of fields. So there's two kinds of composite data in C, structures and arrays. And structures and arrays are deeply tied up with pointers. So we've had a reading about pointers. See, chapter 6 in that C book is about pointers. Chapter 7 is about arrays. Chapter 8 is, chapter 6 is on structure. Their order was pointers, structures, and arrays, but I gave you the reading assignment as pointers, arrays, and structures. Okay, so pointers, arrays, and structures are all just deeply tied together. So I've been giving you reading assignments. Read them as you feel the need to. I mean, they're a reference. As you try to read this code that we're going to be working with, you may have to go back and look at things in those books. It's a lot of material, but hopefully after we explain some things in class, you can go back and you can absorb what you need. You don't need to know everything in these readings, but you do need to know the basics of pointers, arrays, and structs. Okay, pointers, arrays, and structs. That's what our reading is going to be about. Okay, and that's mostly what we're going to need: pointers, arrays, and structs. Okay. All right. So structs and arrays are a general term from is composite data. Okay. Now, so open up this folder. It's working with composite data. These are simple C programs, and the goal. Actually, if I go back to this other folder here, this homework to example folder, there's a README in here. It's a short README. Okay. here's an outline of what we need to know. In order to understand create process, the create process function needs you to understand all of these things. Pointers, functions with in, out, and in-out parameters, which we've talked about. Arrays, struts, arrays of struts. Memory allocation and management, malloc and free. Functions with struts as in-out parameters. So that's tying this idea here. We talked about functions with in-out parameters. We're going to talk about arrays and struts, and then we're going to talk specifically about functions with struts as in-out parameters. That's where create process comes in. Create process is a function with struts as in-out parameters, okay? And also as struts, functions with struts as out parameters, okay? Because they're a little bit different. And when you deal with struts, in-out parameters have their own issues and out parameters have their own issues, okay? And then there's this idea of what's called call by value, okay? So these are the ideas we have to talk about. We have to learn what all these things mean, get comfortable with all these things. Java, to its credit, collapsed all of this stuff into what's an object and what's a reference variable. Yeah, I mean, all of this became simplified in Java as what is a reference variable and what is an object. Okay, which was amazing accomplishment. There's a lot of stuff here in C got simplified by the design of Java. So like a whole bunch of ideas in C, you know, just two ideas in Java. What's an object and what's a reference variable. Okay. So there's an outline of what we want to do. Okay. And then in this working with composite data, there's a little bit more detail about the arrays and struts and the functions of arrays and struts. There's a README here. Okay. The crux of the matter is the following. We want functions to take in big chunks of data. You know, it's how far can you get in life if all your functions take in only ints and doubles? Okay, you're not going to get very far as a programmer if all your functions, their inputs and outputs are ints and doubles. The whole point of real programming is that functions take in large amounts of data and give you back large amounts of data. They take in composite data structures like arrays and struts. So the key is that how do functions work with large amounts of data? In Java, that's not a problem. You don't have to learn anything really particularly special. You just learn what an array, you learn what a reference variable is. A reference variable is a function parameter that points at something, an object. Objects can be as big as you want, okay? So that's about all there is to it. Big data is objects, and you have reference variables pointing to them. But in C, it's way more complicated than that. Okay. Now think about functions that take in an int. When you call a function with an int, you copy the int into the function. Okay. Let me see. I didn't put an example of this. Let's go back. Just do a real simple example. You see what I mean by that? Okay. So if I go to the Java visualizer, let me give myself a real simple function. Okay. Function that just takes in. Okay. Takes in 3 parameters, and I'm not going to do too much with them. I'll just return their sum. Okay. And then I'll call the function a couple times up here. Okay. actually, okay. What happens when you pass simple data into a function? Not composite data, just simple data. And what did I do wrong? Oh. Okay. Okay. When I called this function, I copied that data into that parameter. And I copied that data value into that parameter, and I copied that data value into that data parameter. So you can see over here in F's frame, X is 1, Y is 2, Z is 3.4. But they got copied into there, okay? And then the return value gets copied back into R. So the return value is 4, it got copied back into R. Then A holds 5, B holds 6, C holds 7.8. Now I'm going to call F again. The value of A is looked up here, and then that value 5 gets 5, got copied into, this 5 got copied into X, this 6 got copied into here, and this thing got copied into here. Okay, now let's go back and make it a little bit trickier. String S. Let's suppose it takes a string. I'm not going to do anything with the string. The string's not going to be treated like the ints and doubles. The string's going to be different. Oh. Okay. Now, this is the wrong picture. The Java visualizer is showing me the wrong thing. Does anybody know what's wrong with this picture? We've mentioned, I think, before in class. This is I have to change something in the Java visualizer. This is not the right picture. It's a simple program. What's wrong with the picture on the right?
It says S is hello, even though S is goodbye.
Nope, nope, that's no. This S is which S? This S is not that S. See, we're in F. So this S is what line of code?
Line
what
4.
Pardon me?
Line 4.
No, there's no S on line 4.
It's line 12.
Line 12. See, S is declared on line 12. And we're in F. So we've entered, see, we're down here at 14. So we're using these variables. These are the local variables when we're inside F. So these are the local variables inside F. This S is a local variable inside main. That's one of main's local variables. How come it's not over here under main? Why isn't S under main yet?
Because the variables haven't been created in main yet.
Yeah, in Java, the variable isn't created until you get to the line of code that declares it. See, we're in line 4 of main. Line 4 of main called F. Line 4 of main, there has A, B, C, and S have not yet been declared in main. Okay, but as soon as you enter the function, its parameters are declared. Okay, so S here is that S. Now, where did the hello come from? S comes from line 12. Where does the where does hello come from?
Line 4.
That comes from line 4. See, there's the hello value. The hello value is passed to this S parameter. This guy's called a what?
String literal.
Yeah. What else? Okay, he's a string literal, and he is also, what's another word for that thing?
Object.
What's it got to do with S? What's S called?
String reference.
String reference. And what else? It has another role. So this is a literal, and this is a reference variable. What else? What other role does S have, and what other role does hello have? This guy is a
Variable.
what kind of variable?
Parameter.
Parameter. Yeah, this is a function parameter. Then this is called what? What's the companion to a parameter? What's this thing here stand for?
Arguments.
Arguments. Args. What's an argument?
Value you pass to a method.
Yeah. Is this the right word for this guy? Okay. This is an argument. It's what's passed to the parameter. This is an argument. It's what's passed to that parameter. Should they have called this args?
No.
What should they have called it?
Parameter.
Params. Yeah, but it's the parameter that holds the arguments, the command line arguments. It holds a reference to the command line arguments. We use these words precisely. Command line arguments are the values you put on the command line that are arguments to main. Now here they kind of misnamed this. This is a pointer, a reference to the command line arguments. Okay, but it's actually a parameter. It's a parameter that points to the command line arguments. Okay, so this is an argument for that parameter. This is an argument for that parameter. Okay, what's wrong in this picture over here?
Hello shouldn't be in quotes.
Pardon me?
Hello shouldn't be in quotes.
No, it's a string value. So they show it in quotes. It's a string value. It holds the letter HELLO. So they show it. Yeah, they always, everybody shows string values as being in quotes. That's not the problem there.
There's no pointer.
Yeah, there's the pointer. What is a string? A string in Java is
It's an object.
an object.
I'm thinking of an arrow pointing out of S onto an object.
Right. See, here's the objects. Look, see, here's the objects in their picture. The Java visualizer chooses to show strings as if they were primitives, not objects. If you go back over here and click on options, you can actually say show strings not as values, meaning not as primitives. See, that's a pointer to the object. Now notice that these are not treated like these. In Java, these are called primitive values, and this is called a reference value. This is a primitive variable. Int is a primitive variable type, and string is a reference variable type. String is an example of a composite data. Why is it a composite data?
It's an array of chars.
It's an array of chars. So it's made up of things. It's made up of things. It's not just one thing like an int. It's made up of a bunch of things. So it's a composite thing. In Java, every composite data type is a reference variable, an object with a pointer to it. So some things are copied, which are primitive variables, and some things you copy the reference. Okay, let's go through this. Now watch this. Here's a little bit, watch this one. See this parameter S? When I call main, that S gets copied into that S. So this, see 7.8, that value got copied to there. The value 7.8 got copied to here. What got copied when I passed S to S? What got copied was not the word goodbye. What got copied was a reference to goodbye. This is what C is going to do much more. Java has a uniform rule. Primitives are copied, objects, their references are copied. Okay. Primitives get copied from here, from the function call to the function declaration. This is a function call. This is a function declaration. We have technical words for everything. Okay. Argument, no, parameter, argument, function call, function declaration. Notice there's only one function declaration, but there's multiple function calls. See, there's multiple function calls and only one function declaration. The arguments in the function call are passed to the parameters in the function definition, but they're not passed the same way. Primitive arguments are copied to the primitive parameters. A primitive argument is copied to the primitive parameter. A reference argument is not copied to a reference parameter. A reference argument has its reference value, the pointer, copied. So this pointer got copied to there. There's only one goodbye. Okay. Notice that there's 2 4s, 2 5s, and 2 6. No, I'm sorry. There's 2 5s, 2 6s, and 2 7.8s because they got copied. But there's only one goodbye because these guys are sharing an arrows to it. C is going to take this idea and make it way more complicated. Some things are copied and some things they're shared by a pointer to them. Okay. In C, the rules for this distinction are complicated. In Java, the rules are simple. Primitives are copied, objects are shared. So the primitives are copied from argument to parameter. Objects, when you pass an object as an argument to a parameter, you copy the arrow to the object. Okay. You don't make a copy of goodbye. Now, if you go back here and you uncheck that box, the Java visualizer will really mislead you. See, makes it look like there's 2 goodbyes. Okay. They did that for kind of somewhat good reasons. Because if you do this thing with complicated data structures, the arrows end up being all over the place. And so it's kind of sometimes a little bit simpler just to not show arrows for strings. This is the only thing that they don't show the arrows for. They pretend strings are primitives. They don't do that with other data, with other objects. They only do it with the string object. They pretend strings are primitives. It makes the pictures a little bit simpler, but it's misleading. There are not 2 goodbye strings in memory. There's only one goodbye string over here. So to see that, I have to go back to here, check this box here. Then I get the real picture. There's only one goodbye in memory. It's in the heap, and there's 2 reference variables pointing at it. Okay. Now we want to start seeing how how C handles things like this. Okay. Things that are primitive versus things that are composite. Okay, how does C do this? How does C handle this? Okay, all right. So over here, there's a bit of a discussion of it. In C, these are the rules for C about. There's 2 kinds of composite data types. There's arrays and structs. Strings are arrays. So string is not a separate. C doesn't have strings. C only has arrays of care. So strings fall under the idea of what an array does. Okay. When you want to call a function with an array parameter, what happens? When you want to call a function with a struct parameter, what happens? And the answer is that C will act like Java for the arrays, and struts are treated like primitives. Struts are copies, arrays are not. Arrays are always passed by pointers, but struts are copied, like as if they were primitives. Okay, it's a weird little bit of a choice. And this thing that struts are copied as if they were primitives is one of the things that makes C functions really weird. It's one of the things that makes C hard to understand, because this makes things weird. It actually, we'll see it. And actually also the arrays are done in a really weird way also. I mean, arrays in C are nowhere near as simple as they are in Java. Okay, so let's look at examples. So here's the explanation of it in words, and we're going to just start looking at examples. Okay, so let's look at this code here. Simple strut example. Okay, here's a declaration of a strut. The strut, think of it as a structure. It's called example. It's got 3 fields. This is like a class declaration. Okay, struts are the equivalent of simple classes. So this strut has got 3 fields: an int a, double b, and a char c. Okay, so that's the declaration of the structure of the strut. Okay, here I've declared a variable of type strut example. Okay, there's the variable, there's its type. It is one of these struts. Here's the initialization of that variable. It's initialized to have 5 in the A, 6.7 in the B, and quote 8 in the char. Okay, so this is declaring and initializing a global strut. Java doesn't have global variables. C has global variables. Okay, so I'm declaring an example of a global strut. Now here are local struts. Here's the variable s2. It's a local strut because it's inside main. It's a local variable. So the type of that variable is, notice that you have to put, the name of the type is strut example. You would think it would just be the type is example. S2 is an example variable. S3 is an example variable. But C makes you say the word strut. It's a strut example. Like in Java, you would say, you don't say, like here, okay, my class name is example. You don't declare a variable as class example X, you just say example X. You don't write the word class in front of the word example when you're declaring variables. So if you want a color object, you don't say class color C, you just say color C. But in the C language, you have to essentially say class color. You say strut example. It's just kind of weird. It's an older language. It's got a lot of little quirks to it. So when you declare a variable that's a strut, you say strut name of the strut, then the name of the variable. Okay. Okay. Now this local variable is equal to that local variable. Then this local variable is a pointer to a strut. Then this local variable is another pointer to a strut. Okay. Now what we want to do is we want to picture how these programs grow in memory. The goal of this is going to be for you to read these lines of code and know exactly what they do. Okay. Like this puts a strut in memory for us. This puts a strut in memory, but in a different place in memory. This puts a strut in what's called the global area. This puts a strut in main stack. In main stack, there's going to be a strut sitting in the stack. This creates another strut in the stack, and it copies this one into that one. See, this copies the strut. This one creates a pointer to a strut, and points it at that guy. This one allocates a strut in the heap and then points that pointer at that. So now there's two struts. There's this strut sitting, well, there's this strut sitting in the global area. This one's sitting in the stack. This one's sitting in the stack. So that's three struts. This is a pointer at one of the struts in the stack. And this is a pointer to another strut in the heap. Now we got struts in three different locations. One in the global area, two in the stack, and one in the heap. And we have to start, as C programmers, that has to be part of your mental map of a program. What's in the global area? What's in the stack? What's in the heap? Because it really matters. Okay, who's sitting where? In this outline here, that was this idea of memory allocation and management. That's number 6, understanding memory allocation and management. Where is the memory for a variable been allocated? It's either in the global area, the stack, or the heap. Okay, there's 3 areas: global, stack, and heap. Java only has stack and heap. Java got rid of the global thing. So only got stack and heap. But Java introduced something called static variables, which are the closest thing that Java has to global variables. So Java really does have 3 things too. It's got local variables, heap variables, and then these things called static variables, which are neither in the heap nor in the stack. So they're kind of weird. So C has heap, stack, and global. Java has heap, stack, and static. But the static variables are not global variables. Okay. All right. So we have to understand this allocation and management. Notice that this is a simple example, just a few lines of code, but we have to really understand it line by line. Your goal is to read this code and know exactly what it does line by line. And by saying know exactly what it does, I mean draw a picture. And we're gonna have this website draw the pictures for us. You should be able to draw a picture of this code. Real programmers draw the picture in their heads. They all draw pictures. Real programmers draw pictures. Just that people who are experienced can draw them in their head. When you're starting out, you have to draw them on paper. And believe me, I draw plenty of pictures on paper when I'm writing complicated code. It doesn't matter if it's in C or Java or C++. I almost always draw myself lots of pictures. You need to know how your program looks in memory. You should always be drawing pictures until you're so comfortable with this stuff that the pictures just appear in your head automatically. You should be drawing pictures. And that's why they invented the Java visualizer and the C visualizer, because they realized that students need a tool to help them draw these pictures. That's one of these websites I think are fantastic. They really help. This is really useful. You should be doing this in your head automatically. Okay, but they do it for you to train you. But this is not a crutch. This is not what this is the thing that shows you what you should be doing yourself. You use this to train yourself on how to think about objects and reference variables and how parameter passing. Okay, so we're going to do the same thing in C now with this other example. Okay, so I want to go to that website. Okay, and I want to copy and paste this code into it. Okay, and I'm going to visualize this code, and it's going to draw the nice pictures for me. Okay. Oh, I dropped that. I forgot to put that back in there. I should, put it back in here too. Okay, forgot to put that back. Okay, so okay. All right, now things get messier in C. Here's my code that I'm stepping through. Here's where output will be if I do any printfs. They'll show up over here. Here is memory. stack and heap, but they did something kind of weird. They showed the global variables as if they were under the stack, and they shouldn't have done that. They probably should have put the global variable up here in the corner. I'm not sure. I think they did a very confusing thing here. The stack is where the function calls are going to be. See, okay, we have this function main. See, we're at the beginning of main. We're at line 13. So main's local variables are on the stack. Really think of this as floating over here. It's a separate area of memory. So the heap is this right half of the picture. The stack is the left half of the picture, which is very much like the Java visualizer. Okay. They use the word frames where it really should have been called stack. I mean, these things are called stack frames. This square box here is often thought of as a frame. That's a technical word that comes out of compiler people. So I don't know why they chose to use that word over here. Frame is a word that's mostly used by compiler people. They call this a stack frame. It's, here they use the better word. They just call it the stack. And then this blue box here is a stack frame. This box here is not part of the stack. Again, it's part of the global variables. It's its own region over here, okay? Then see how this is called objects. Well, in Java, objects are always in the heap. So here, that's the same thing as the heap, okay? This is the stack and this is the heap. I wish they had called this stack and heap in the Java visualizer, but for some reason they call them frames. And I mean, objects is what is over here. In the heap are objects. Over here in the heap is anything you want to put in there. Okay, here they would never say objects because the heap is anything you want to put in the heap. You can put primitives in the heap if you want. In Java, you cannot put a primitive in the heap. So you can only put objects in the heap. In C, you can put anything in the heap. We'll see it. We'll put up int in the heap later on. Okay, so the heap is where you can put your own variables in the heap. Okay, and so you have the stack is where your local variables are, and the heap is what you put in there in C. We'll see how you do that. Okay, so there are three areas of memory: are the heap, the stack, and the global variables. And really, that should have been over here. Okay, now notice that remember I said let's go backwards and see. I'm at line 5. When I execute line 5, A shows up. When I execute line 6, B shows up. That's not how C does it. The way they think of it in C is when I enter the function, all the local variables are allocated on the stack. So there's all my local variables. See, there's my S2, S3, S4, S5. All my local variables are in the stack. But what do all those question marks mean? See, I'm still at line 13. So
It doesn't know what the data type is in there?
No, it knows the data type.
What data, sorry.
Right, they're not initialized yet. Nothing's been put in them yet. They're allocated, but not initialized. In Java, they don't allocate until they initialize the variable. So until you get to line 7, C doesn't exist. As soon as C exists, it's been allocated and initialized simultaneously. Okay, that's Java's way of thinking. You allocate and initialize simultaneously. In C, well, the way they think of it is you allocate when you get to the beginning of the function. So all the variables are allocated, but they're not initialized until I get to the line of code that, supposedly this line of code, like line 14 supposedly allocates S2 and initializes it. But the way C thinks of it is that it's allocated as soon as you get to line 13, but it's not going to be initialized until you get to line 14. So step to line 14. Now watch S2 gets initialized. Now get to line 15. Now that's going to take all the fields of S2 and copy them into S3. So this stuff is going to get copied down here. Now notice these are composite data structures sitting in the stack. Java won't let you do that. The only thing that can be in the stack are primitives or pointers to composite data. I cannot put goodbye in the stack. or any other object. I can't put composites into the stack in Java, but in C, yeah, there's a composite data structure sitting in the stack, not in the heap like it would be in Java. Java would have put this composite thing in the heap automatically and then created this as a pointer to it. If you want something to point to something in the heap, well, okay, now watch this one. Next one's tricky. Okay, now we get to S4. S4 is a pointer to a strut. It's going to point at S3. Notice it's not pointing into a heap, it's pointing into the stack. Notice in Java, you can only point into the heap. You can't point from one place into the stack into another place in the stack. Java will never do that. You can never, because you can never have composite things in the stack, so you can never have something in the stack pointing at something in the stack. Composite things are always in the heap, so pointers always point into the heap. But C lets you do all kinds of weird things. Actually, in C, this is not even considered weird. The strut is in the stack because it's a local variable, and now I've got S4, which is a pointer variable pointing at a structure in the stack. Now, this is the line of code that puts something in the heap. Memory allocate, malloc in the heap, the number of bytes in a strut. Okay, so there's the data type. I want the size of that data type. I need to allocate enough bytes to hold the strut example. Malloc returns a pointer to a generic object, so I have to cast its pointer to a pointer to strut example. So this is a cast. So I'm casting the return value from malloc to a pointer to what I just created space for. So next, okay, there's space for a strut. Notice it's only space for a strut. It's not what?
Initialized.
Yeah, it's not a strut value yet. Malloc only creates space for a strut. Malloc is like a really lousy constructor. What do constructors in Java do? Give you a hint. They do two things. Constructors do what?
Allocate and initialize.
Yeah, and you write the code to do that. The allocation is done automatically, and then your constructor code says, and here's how to initialize the data. C doesn't have constructors. There's no such thing as a constructor in C. There's only malloc. Malloc allocates space, but doesn't put anything in the space. So if I want to put something in there, I have to do it myself. I have to put something in that A, put something in that B, and put something in that C. So the pointers initialize the point to that memory, but that memory is uninitialized now. So I've got 4 struts, 1 in the global area, 2 in the stack, and 1 in the heap. Okay. All right. Now I'm going to print them. Okay. And the way I'm going to print them is I'll just access their fields. Like I'm going to print a double, a float, and a char. S1.A, S1.B. There's no toString methods in C. So if you want to print a strut, you have to do it more or less by yourself that way. So print the strut. Okay, see, I printed, that was the strut in the global area. Print the next strut, that's the strut S2. Print the next strut, that was S3, that's this guy here. Now, here, I want to print what's over here. I'm sorry, I want to print what S4 points at this thing. Notice how on S3, to get A, the A field of S3 is S3.A, right? Just like in Java, dot notation. S3 is the variable, dot A is the field. Now look, at this one's tricky. S4 is a pointer to a strut. If I want the A in it, I don't write S4.A, I write S4 arrow A. S4 is a pointer. So the notation's kind of reminding you, you have to follow the pointer to the object, then get the A field in the object. So it's S4 arrow A, not S4.A. Okay, so that's, you gotta remember that notation. S4 arrow A. When S4 points at a strut, you follow the pointer to the strut and then get the field. Okay, so that will then do that and print out that strut there again. Okay, now S5 points to this guy. The visualizer stops me on an error. I'm trying to access uninitialized data. One thing that's interesting is that's not part of the C language. The C language does not stop you if you access uninitialized data. The C language, if this was a C program running on my computer, it would just go jump in there and grab whatever garbage is in that variable. There actually isn't a question mark in there. There's some garbage value in there. There's a garbage value in there, and there's a garbage value in there. The visualizer stopped me from, it's trying to help you write better code. So it stopped me from accessing an uninitialized piece of data. Okay, a real C program running on your computer, if you compiled this program over here, if you compiled this thing using our, well, open command window here. Our compiler is in the C:/CS302 folder. It's in the min.gw folder in the bin folder, and its GCC is the compiler. I want to compile this program, simple string example, and I want the output to be .exe, and I want to compile simple string example. Okay, so I just compiled it. Okay, now I can run it. I'm going to run the exe version. Okay, notice it didn't. Yeah, does anybody see where the bizarreness is? Oh, I did. I compiled the wrong one. Stupid me. I compiled the wrong one. I want the simple strut example. Okay, so simple strut example and simple compile the other one. Now run the other one. Okay, run it. Okay, now compare that output to what the visualizer was showing us. There's the visualizer's output. There's our output running it. Okay, those same. Then we get to what should have been the uninitialized strut. Notice that the C program couldn't care less if it's uninitialized. So what did it print out? Very weird numbers. See, it just printed out the garbage that's actually sitting in this strut. So it printed out really strange stuff. If I run it again, I might actually get, oh no, I got a different answer this time. This one is different. This one turned out to be the same, but I got a different number over here. If I run it again, I got a different, some reason I'm getting the same answer here, but I'm getting a different thing over here. Okay, but I'm printing garbage now. Notice that C programs don't care if you initialize values or not. Real C programs blast right through uninitialized data and print whatever garbage is in them. The visualizer, being a more sophisticated system that's meant for educational purposes, it's checking. It kept track of the fact that this is uninitialized, and it said when you got to that line of code and you tried to print the uninitialized data, it stopped you. Okay, but a real C program, and this is one of the reasons why real C programs can be hard to debug. If you create a variable and don't initialize it, you just get garbage in there. So every time you run the program, it runs differently, and it can be real hard to debug this stuff because every time you run the program, something different happens. You know, because it's playing with uninitialized variables, which basically just have random values in them. Okay. All right. Notice how every line of code does something to our picture, and we want to understand the picture. We want to know what these lines of code does. That allocated a strut in the stack. That allocated a strut in the stack and copied this one into that one. This created a pointer variable in the stack and pointed it at that structure in the stack. This allocated an uninitialized structure in the heap and pointed that local variable to it. Okay. Oh, and this created a structure in the global area. Okay, now we're not even talking about functions yet. See, we're just trying to understand the variables. We haven't even gotten to functions yet. Okay, now let's do the same thing with the string one. In this folder, there's a simple string example. There's this simple string example. It's very similar to the strut example, but it uses an array, which is a string. Okay, so I'm going to copy and paste this into I'm going to bring up another instance of the visualizer. Okay, this is supposed to parallel this one about as closely as possible to show you how strut composite data and array composite data can look a little bit different. Okay, so this creates an array in the global area. This one created a strut in the global area. This one creates an array in the global area. Then this creates an array in the, this is going to create an array in the stack frame, in the stack. Okay, this is going to create another array in the stack, just like these two were created. This was created in the stack, and this one was created in the stack. Okay, this one's going to create an array in the stack, and this one's going to create an array in the stack. This one's going to create another array in the stack. This one's going to create an array in the heap, okay, and point at the array in the heap, okay. And this one's going to create a pointer that points to that string in the stack, okay. This is going to initialize the one that's in the heap. No, this is going to initialize the one that's in the stack. This is creating an uninitialized array in the stack, and then this initializes it, and then it tries to print things. Okay, so visualize this. So, okay, yeah, see, it died out. Sometimes when it dies like that, I'm just going to copy and paste and create a new tab. I'm just going to launch it over again. See if it probably doesn't need to be. Let's hope that this time it goes. There, okay. Their server is probably a little loaded. Okay. I'm at line 7 of main. There's the local variables in main. They've been allocated but not initialized. That global variable has been initialized, allocated and initialized, okay? And then as I step through, this initializes that array. Then this initializes that array with just a different notation. There's two different ways of initializing a string. Almost nobody uses the second one. You almost always use the first one, okay? Okay, now I'm going to allocate in, okay? I allocated memory in this heap and pointed a pointer at it, okay? And then I created a pointer points at that thing in the global area. So I got one pointer pointing in the heap and one pointer pointing in the global area. Notice I didn't create a pointer into the stack this time, okay? In the other one, I created a pointer into the stack. This time I created a pointer into the global area, okay? And then now I'm putting things in here. Okay, now I'm putting things in here. See, I followed this pointer over to here, and but notice that I didn't use pointer notation. I used array notation. Array notation is a synonym for pointer notation. That's one of the differences between struts and arrays. When you use struts, you have to explicitly use pointer notation. With arrays, you can use array notation, which hides the pointer notation. Okay, and then if I print these, I get the same kind of problem. When I get to printing something that's uninitialized, I get an error message. Okay, now these two examples look a lot alike because we're not using functions yet. The difference between structs and arrays shows up when they become function parameters. Okay, so the code we're looking at here are simple. There's no functions. So the strings and the struts act a lot alike. But when we get to working with functions, these other examples down here, these ones have functions, then things start really changing. So that's what we'll do on Wednesday. We'll make these pictures be more elaborate because we'll start doing what we did with the Java example. In the Java example, we had a function. So we want to see how do the function arguments get passed. C is complicated enough that just understanding the local variables is tricky. So what we did here is we understood local variables in C. Then we want to study parameters in C. Okay, so you can see already local variables in C are already tricky because they can be in the global area, they can be in the stack, they can be in the heap. Local variables are already a problem. Then the next issue is how do function parameters get handled in C? So first local variables, then parameters. In Java, local variables are trivial and function parameters are pretty trivial too. They're either primitives and they get copied, or they're reference variables and the arrow gets copied. Okay, they're either primitives that get copied or the reference variables, arrows that get copied. Only two things to worry about, primitives and arrows. In C, it's going to be way messier than that. Arrays are going to be treated one way, or struts are going to be treated another way, except that when arrays are in struts, they're treated a different way. And it's just going to be, it's messy. And we do need this because if you do any programming in C with Windows or Linux, you get functions like create process that we were looking at earlier. You get functions like create process that does this stuff. Okay, you can't avoid this stuff because of functions like create process. Everything we're talking about is going on here and in here. And this is hard to read. So by looking at simple examples, we're building up how to read this, how to read this, and how to read this. Because it's not a trivial thing to read and not a trivial thing to write. These are the local variables. These are the parameters. We want to go from how do local variables work to how do parameters work. Okay, so we run out of time. Download these examples and play with them. Your goal is to be able to read these programs and understand what they do line by line. Notice the programs are not very long. Literally start at that line of code. What does it do? Watch it in the Java visualizer. What does that line of code do? Watch it in the Java visualizer. What does that line of code do? And when I say what does it do to memory? Does it move things around? Does it copy? Does it move a pointer? Does it what does that line of code do in the picture? There's a function call. What does that function call do in a picture? Read it line by line. Okay, we'll quit there. All right. So if you have questions about this stuff, send me email. Read these examples real carefully. That's your reading assignment is this code, line by line. And you like I say up here, put it in the visualizer and watch it. Go back and forth. Predict, watch. Predict, watch. Try to predict, then watch what happens. Try to predict, then watch what happens. Okay. All right. So that's what we'll be playing around with on Wednesday. Okay. Anybody have any last second question? Any last second question what we've been talking about?
When's the homework due?
Up here, next Wednesday, I think I'll move it to next month, 2 weeks from today, because we're just starting to talk about this stuff. So I'll move it to this month, 2 weeks from today, because you have to really start understanding the C stuff before you can start writing that assignment. So on Wednesday, we'll cover a little bit more of the C stuff, but you have to read these reading assignments in C and follow this code to be able to use it to write this stuff here. Okay, so I'll make it do, I'll update that to, oh, I lost the page now. I'll update that to next Monday, two Mondays from now. It'll be two
Okay.
Mondays from now, okay? Other questions about the homework or what we talked about? It's hard stuff. Don't believe me. You need all 2 weeks to figure this stuff out. You will not get anywhere in 2 days on this. Do not let this go till the last minute. You'll get nowhere. This is pretty hard unless you've written C code before, unless you've written this kind of C code before. And this is not the kind of C code you find in your C++ textbook either. Unless you've written this kind of C code, it's tricky. It takes real effort to write this kind of code. Okay, so it takes effort to study that many lines of C and be able to say what each line does. So start reading this stuff now. It needs to soak in slowly over time. Okay, so your reading assignment is really this C code for now. Okay, any last question? Anything? Okay, so I'm gonna stop the sharing and we'll meet again on Wednesday, okay? And if you have questions, send me email. Bye.